Now in this lecture I'll answer two questions. In the first question we find out the area of this green shape that inside square T is QP, and in the second question we find out the area of this green shape that is inside square ABCD. So we start with the first question. In the drawing we have two squares. We have the big square TSQP, the small square ABCP. In addition, we know that this is triangle AMP. This is equals to 9 square units in its length. This is quadrangle ABCP. This is equals to 27 square units in its size. Again, our task is to find out the area of this green shape. This is triangle AMP. This is equals to 9 square units in its size, and this is quadrangle ABCP. This is equals to 27 square units in its size, and our task is to find out the area of this green shape. So first of all, we know that the small square ABCP in total it is equal to 9 plus 27, that is 36 square units. So I have to know the small square ABCP total it is equal to 36 square units in its size from one side, but from the other side we know that the area of any square equals to the length of one side squared, and therefore the area of this square ABCP will be equal to the length of side AP squared. So it is AP squared. Repeat again. From one side, square ABCP equals to 9 plus 27, that is 36 square units in size, but from the other side, the area of square ABCP equals to AP squared. From this equation, AP squared equals to the square to the area of square ABCP equals to 36. We know that AP squared equals to 36. Here we will take out of this equation and get that AP equals to the square root of 36, that is 6. So AP equals to 6 units in its length. This is side AP. This is equals to 6 units in its length. It is given as a question that this is triangle AMP. This equals to 90 degrees in its size. In the small square ABCP, we know that all the angles are equal to 90 degrees. So this angle must be equal to 90 degrees in its size. It is 1 out of 4 angles of the small square ABCP, and therefore it must be equal to 90 degrees in its size. And therefore triangle AMP is equal to the right triangle AMP is the right triangle, and it is equal to 9 square units in its size. And the area from one side, the area of the right triangle AMP equals to 9 square units in its size. But from the other side, we know that the area of any triangle equals to the base of the triangle times the height over 2. So the base is AM. The base of the right triangle AMP is AM times the height AP over 2 is the area of this right triangle AMP. But again, from one side, the area of the right triangle AMP equals to the base AM times the height AP over 2. From the other side, it is given us the question that the area of the right triangle AMP equals to 9 square units in its size. And for this equation, AM times AP over 2 equals to the area of the right triangle AMP equals to 9. We will derive that AM, that those two sides are equal to each other. AM times AP over 2 equals to 9. AP equals to 6, so we substitute AP by 6 in this side of the equation, and we get that AM times 6 over 2 equals to 9. 6 over 2 is 3, so 3 times AM equals to 9. Here we will divide this equation by 3, and finally get that AM equals to 9 over 3 is 3. AM equals to 3 units in its length. This is side AM is equals to 3 units in its length. In order to find out the length of side MP of the right triangle AMP, we'll implement the Pythagoras theorem on this right triangle AMP. So I copy the right triangle AMP in a new page and we will implement on it the Pythagoras theorem. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the sides of the perpendiculars. This is the right triangle AMP. This is the common from the original drawing. This right triangle AMP. MP squared, that is the square of the hypotenuse, equals to AP squared plus AM squared. MP squared, this is the square of the hypotenuse, equals to AM squared plus AP squared. MP is the missing side, so we leave it as it is, so it is MP squared equals to AM squared. AM is 3, therefore AM squared is 3 squared, it is 9, plus AP squared. AP is 6, therefore AP squared equals to 6 squared, that is 36. So in total, MP squared equals to 9 plus 36, that is 45. So MP squared equals to 45. Here we substitute 45 by 9 times 5 and get that MP squared equals to 9 times 5. Here we'll take a water out of this equation. And finally we get that MP we see that hypotenuse MP equals to the square root of 9, that is 3. Inside the root we left only with 5. So in total we found out that MP equals to 3 times square root of 5 units in its length. This is side MP. That equals to 3 times square root of 5 units in its length. What is the length of the missing line segment MB? MB equals to AB minus AM. So now MB equals to AB minus AM. MB equals to, we know that all the sides of the small square ABCP are equal to each other. AP equals to 6, therefore AB must be also equal to 6, so AB equals to 6 minus AM. AM is 3, so in total MB equals to 6 minus 3, that is 3. So MB equals to 3 units in its length. Those two angles are defined as vertex angles, and we know that vertex angles are equal to each other. So if you define the side of this angle as alpha, then the side of this angle must be also equal to alpha because they are equal to each other, according to the rules I mentioned. So in the big right triangle AMP, this angle equals to alpha, this angle equals to 90 degrees, and therefore this angle must be equal to 90 degrees minus alpha. Well, we put 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is 180 degrees. That is the sum of the angles in a triangle. Likewise, in the small, first of all, we know that all the angles inside any square are right angles. So, in the big square DSQP, this angle is 1 out of 4 angles of square ABCQP, and therefore it is equal to 90 degrees in its size. So, in the small right triangle TBM, this angle equals to alpha, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus alpha. According to the sum rule, that the sum of the angles in any triangle is equal to 180 degrees. In the next step, we prove that those two right angles are similar to each other according to angle similarity rule. That is to say, we prove that the small right triangle TMB is similar to the big right triangle AMP according to angle similarity rule. So write those two right triangles are similar to each other. First of all, those two angles are both equal to alpha, therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees, and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. Well, so I should prove that all the triangles of the big right triangle AMP are correspondingly equal to all the triangles of this small right triangle TMB, and therefore those two right triangles are similar to each other according to angle similarity rule. So I write it down. So I should prove that the big right triangle AMP is similar. This is the sign of similar to the small right triangle TMB according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We derive the side AP of the big right triangle AMP. And again, we derive the side AP of the big right triangle AMP over side TB of the small right triangle TMB. equals to side AM of the big right triangle AMP over side TM of the small right triangle TMB, and it is also equals to side MP of the big right triangle AMP over side MB of the small right triangle TMB. And again, from the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We derive that side AP of the big right triangle AMP over side TB of the small right triangle TMB equals to side AM of the big right triangle AMP over side TM of the small right triangle TMB, and it is also equals to side MP of the big right triangle AMP over side MB of the small right triangle TMB. AP equals to 6 over TB. TB is the missing side, so we'll notice it is. And it is equal to AM. AM is 3 over TM. TM is the missing side, so we'll notice it is. And it is equal to MP. MP is 3 times square root of 5 over MB. MB is 3. So in total, we actually found out that 6 over TB equals to 3 over TM equals to 3 times square root of 5 over 3. So here we have 3 in the numerator and 3 in the denominator, so 3 will get cancelled. We left only with square root of 5. So in total, we found out that 6 over TB equals to 3 over TM equals to square root of 5. So now we found out that 6 over TB equals to 3 over TM equals to the square root of 5. Those two sides are equal to each other, and therefore we can equation one from those two sides that are equal to each other. That is to say, 6 over TB equals to the square root of 5. Here we multiply this equation by TB, and then we divide it by square root of 5, and we get that TB equals to 6 over square root of 5 units in its length. So this is the missing side TB. It equals to 6 times square root of 5 units in its length. 6 over square root of 5 units in its length. Likewise, those two expressions are equal to each other, so you get the second equation from those two expressions that are equal to each other. So 3 over Tm equals to square root of 5. Here we will multiply this equation by Tm, and then we will divide it by square root of 5, and we get that Tm equals to 3 over square root of 5 units in its length. This is side Tm is equals to 3 over square root of 5 units in its length. Our task is to find out the area of this green shape. So, what is the area of the green shape? On the drawing, it is very easy to see that the area of this green shape equals to the area of the big square TSQP minus the area of this quadrilateral MBCP minus the area of this right triangle TMB. So write it down. The area of the green shape equals to the area of the big square TSQP minus the area of this quadrilateral MBCP. According to what is in the question, the area of quadrilateral MBCP equals to 27 square units in its size. So minus the area of quadrilateral MBCP minus the area of this small right triangle TBM. Because again, if you found out that the area of this green shape, in total it is equal to the area of the big square TSQP minus the area of quadrilateral MBCP. This is equal to 27 square units in size according to what is given in the question, minus the area of the right triangle TBM. So the area of the big square TSQP equals to the length of one side squared. So we find out the length of side TP, we square it, and this will be the area of this big square TSQP. What is the length of TP? TP equals to Tm plus MP. Again, TP equals to Tm plus MP. Again, TP equals to Tm plus MP. So TP equals to Tm. Tm equals to 3 over square root of 5. Plus MP. MP equals to 3 times square root of 5. So in total, we will know that TP equals to Tm, that is 3 over square root of 5, plus MP, that is 3 times square root of 5. So TP equals to 3 over square root of 5. Here we multiply this number by square root of 5 and then divide it by square root of 5 in order to have a common factor with this number, and we get that 3 times square root of 5 times square root of 5 is 5, and 5 times 3 is 15, so the numerator we have 15 divided by square root of 5. So in total we found out that TP equals to 3 plus 15, that is 18, over square root of 5 units in its length. And again, TP is equal to 18 over square root of 5 units in its length. So one side of the big square TSQP equals to TP, and therefore the area of square TSQP must be equal to TP squared. So the area of the big square TSQP equals to TP squared, that is the length of one side squared, minus the area of quadrangle MBCP. Quadrangle MBCP equals to 27 square units inside, according to what is given in the question. So it is minus 27 minus the area of the right small triangle TBM. The small right triangle TBM, the area of this small right triangle TBM equals to the base TB times the height TM over 2. So the area of the green shape equals to the area of square TSQP. The area of square, the big square TSQP equals to TP square. TP, we already found out that TP equals to 18 over square root of 5, and therefore TP squared must be equal to 18 over square root of 5 squared. Minus 27 minus the area of small right triangle TBM is equals to the base TB. The base TB equals to 6 times square root of 5, 6 over square root of 5 times the height TM. The height TM equals to 3 over square root of 5 units in its length, divided by 2. So in total, the area of the small right triangle TBM equals to TB, that is 6 over square root of 5, times TM, that is 3 over square root of 5, divided by 2. TP squared is 18 over square root of 5 squared. 18 squared is 324 over square root of 5 squared. Square root of 5 squared is 5. So in total, the area of the big square TSQP equals to 324 over 5 square units in its size. Minus the area of quadrangle MBCP, that is 27, minus the area of the small right triangle TBM, that is equal to this expression. So in the numerator we have 6 times 3, that is 18, over in the denominator we have square root of 5 times square root of 5 is 5, and 5 times 2 is 10. So in total, the area of the small right triangle TBM equals to 18 over 10 square units in its size. (324 over 5 is 64.8 minus 27 minus 18 over 10 is minus 1.8. So in total, the area of the green shape equals to 64.8 minus 1.8 is 63. So in total, we have here 63 minus 27. 63 minus 27 is 36. So in total, we should know that the area of this green shape, that is the area that we are looking for in this question, is equal to 36 square units in size. Is equal to 36 square units in its size. So I finish with the first question. In the next step, I present to you the second question, and we solve the second question of this lecture. In the second question, our task is to find out the area of this vein shape. So in the drawing, we have square ABCD. We know that one side of square ABCD is equal to 10 units in its length, and therefore all the four sides of square ABCD must be equal to 10. In addition, inside this square ABCD, we have this semicircle and this quarter circle. BC is one side of square ABCD, but BC is also the diameter of the semicircle. When we find the center of this semicircle, this point is point O. The diameter on the semicircle BC is 10, and therefore the radius must be equal to 10 over 2, that is 5. So the radius OB is 5, and the radius OC is also 5. In the next step, likewise, we know that point A is the center of the quarter circle, point B is the point on the quarter circle itself, therefore AB is the radius of the quarter circle, that is 10. Likewise, AD is also the radius of the quarter circle, that is equal to 10 units in its length. In the next step, we'll define the intersection point between the quarter circle and the semicircle. This point is point M, and we'll join points A and M together by a straight line. Point A is the center of the quarter circle. Point M is the point on the quarter circle itself. Therefore, AM is the radius of the quarter circle. This equals to 10. So actually, line segment AM is tangent to the semicircle at point M. Again, line segment AM is tangent to this semicircle at point M. Point M is the point of tendency of line segment AM in this semicircle. In the next step, we'll join points O and M together by a straight line. Point O is the center of the semicircle, point M is the point on the semicircle itself. Therefore, OM is the radius of this semicircle. This is equal to 5 units in its length. Here we can implement rule 1. Why? Because the radius OM of the semicircle that equals to 5, the radius OM is drawn to point M, that is the point of tendency of tangent AM with this semicircle. And whenever you have radius that is drawn to the point of tendency, then tangent AM will be perpendicular to the radius MO. If AM is perpendicular to MO, it means that this angle equals to 90 degrees in its size. According to rule 1, of course. We know that all the angles inside the square are right angles. And therefore, this is angle ABC, that is a right angle. This is one out of 4 angles of square ABCD, and therefore it is equal to 90 degrees in its size. In the next step, we will join points A and O together by a straight line. By joining points A and O, we can determine two right angles. This is the right angle AMO, and this is the right angle AOB. So, in the next step, we'll prove that those two right angles can go into each other according to side rule. So, I write it down. We prove that the right angle AMO can go into the right angle AOB according to side rule. So why those two right triangles can go into each other? First of all, side OB of the right triangle ABO equals to side OM of the right triangle AOM. They are both the radii of the semicircle is equals to 5, and therefore they are equal to each other. So OB equals to OM equals to 5. Okay, again, side OB of the right triangle AOB equals to side OM of the right triangle AOM. They are both the radii of the semicircle is equals to 5, and therefore they are equal to each other. In addition, side AB of the right triangle AOB equals to side AM of the right triangle AOM. They are both the radii of the quarter circle that is equal to 10, and therefore they are equal to each other. So already known. Okay, again, side AB of the right triangle AOB equals to side AM of the right triangle AOM. They are both the radii of the quarter circle that is equal to 10, and therefore they are equal to each other. And finally, AO is a common side that belongs to both triangles, so I can write down that AO equals to itself. It's a common side that belongs to both triangles. So if you prove that all the three sides of this right triangle AOB are correspondingly equal to all the three sides of this right triangle AOM, and therefore those two right triangles can go into each other according to side rule. Okay, now the right triangle AOB congruent. This is the sign of congruent to the right triangle AOM according to side rule. And from the fact that those two right triangles can go into each other, we derive that those two angles must be also equal to each other, according to the rule that corresponding angles in congruent triangles are equal to each other. Those two triangles can go into each other, and therefore those two corresponding angles must be also equal to each other. So if we define the size of this angle as alpha, then the size of this angle must be also equal to alpha, because they are equal to each other according to the rule that I mentioned. Likewise, from the fact that those two right triangles can go into each other, we derive that those two angles must be also equal to each other according to the same rule that corresponding angles in congruent triangles are equal to each other. So if we define the size of this angle as beta, then the size of this angle must be also equal to beta, because they are equal to each other according to the rule that I mentioned. In the next step, we'll implement the Pythagoras theorem on the big right triangle AOB. So I copy the right triangle AOB in a new page, and we'll implement on it the Pythagoras theorem in order to find out the length of the hypotenuse AO. Here by PT is abbreviation for Pythagoras theorem. So this is right triangle ABO that according from the original drawing, this right triangle ABO, AO squared, that is the square of the hypotenuse, equals to AB square plus BO square. So I write it down. AO square, that is the square of the hypotenuse, must be equal to AB square plus BO square. AO is the missing side, so it is AO square equals to AB square. AB is 10, therefore AB square is 10 squared, that is 100, plus BO square. BO is 5, therefore BO square is 5 squared, that is 25. So in total we should found out that AO square equals to 100 plus 25, that is 125. AO square equals to 125. Here we will substitute 125 by 25 times 5, and we get that AO square equals to 25 times 5. Here we take out all of this equation, and finally we get that the left side AO, the opposite AO, is equal to the square root of 25, that is 5, so inside the root we left only with 5. So in total we found out that AO equals to 5 times square root of 5 units in its length. This is side AO, that equals to 5 times square root of 5 units in its length. Note that all the angles inside any triangle, the sum of the angles inside the triangle must be equal to 180 degrees, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. So which angles we have in the right triangle ABO? We have alpha plus beta plus 90 degrees. In total, the sum of those angles must be equal to 180 degrees. Repeat again. In the right triangle ABO, the sum of the angles must be equal to 180 degrees. So alpha plus beta plus 90 degrees, in total it must be equal to 180 degrees. Here we subtract 90 degrees from this equation, and we get that alpha plus beta equals to 180 degrees minus 90 degrees is 90 degrees. So alpha plus beta equals to 90 degrees. Here we subtract alpha alpha from this equation, and we get that beta equals to 90 degrees minus alpha. And again, I should find out that beta equals to 90 degrees minus alpha. We'll continue to focus on the right triangle ABO. In the right triangle ABO, sinus alpha equals to BO over AO. And again, in the right triangle ABO, sinus alpha equals to BO over AO. Repeat again. In the right triangle ABO, sinus alpha equals to BO over AO. BO is 5 over AO. The hypotenuse AO equals to 5 times 4 for 5 units in its length. So in total, we have found out that sinus alpha equals to 5 over 5 times 4 for 5 units. So sinus alpha equals to 5 over 5 times 4 to 5 units. Here we have 5 in the numerator, 5 in the denominator, so 5 will get cancelled, and we left only with 1 over square root of 5. So in total, we shall find out that sinus alpha equals to 1 over square root of 5. Our task is to find out the value of angle alpha itself, or the size of angle alpha. In order to find out the size of angle alpha, we'll operate the opposite function of sine, that is arc sine, on the result of sinus alpha, that is 1 over square root of 5. In this way, we find out the size of angle alpha. And again, the opposite function of sine is arc sine. We operate the opposite function arc sine in the result of sinus alpha, that is 1 over square root of 5, and it will be equal to angle alpha itself, the size of angle alpha. Arc sine 1 over square root of 5 is actually 26.565 degrees. So 26.565 degrees equals to alpha. So alpha equals to 26.565 units in 26.565 degrees in its size. And therefore 2 alpha must be equal to 2 times 26.565. So it is equal to 53.13 degrees. Again, I should find that the 2 alpha equals to 53.13 degrees. The big angle MAB equals to alpha plus alpha, that is 2 alpha, so angle MAB equals to 53.13 degrees in its size. We have already found out that beta equals to 90 degrees minus alpha. We found out that beta equals to 90 degrees minus alpha. So beta equals to 90 degrees minus alpha, and alpha is 26.565 degrees. 90 degrees minus 26.565 degrees is equal to 63.435 degrees. So angle beta equals to 63.435 degrees in its size, and therefore 2 beta must be equal to 2 times 63.345. This is actually 126.87 degrees in its size. And again, I shall find out that the big angle MOB, this is the big angle MOB, is equal to 2 beta, and 2 beta equals to 126.87 degrees in its size. Our task is to find out the area of this green shape. In order to find out the area of the green shape, we will join points M and B together by a straight line. By joining points M and B, we divided the green shape into 2 parts. The first part, this is the first part, so we'll define the upper part, this is actually a segment. We define the upper segment, a segment BUM. This is the upper segment BUM. And we'll define the lower segment. This is the lower segment, a segment MLB or BLM. This is the lower segment, this is BLM. And there we'll calculate the area of each segment separately, and we'll add the two areas with each other, and it will be equal to the area of the green shape. That is the area that we're looking for in this question. So first of all, we find out the size of the lower segment MLB. This is the lower segment MLB. In order to find out the size of the lower segment MLB, I'll copy sector ABM. In your question, you analyze this sector ABM. This is angle 2 alpha. We already found out that 2 alpha equals to 53.13 degrees. This is sector ABM, the decorated from the original drawing. The rounded sign above ABM is a sign for a sector. It means sector ABM. So, first of all, what is a sector? A sector is a portion of a circle enclosed by two radii and the arc between them. The green shape AOB is the sector because we know that it is a portion of a circle, a portion of this circle enclosed by two radii. Those are the two radii of this circle, and arc AB between the two radii. So repeat again, the sector is a portion of a circle enclosed by two radii and the arc between the two radii. The two radii are defined as the legs of the sector. So this is angle theta. This is the legs between the angle between the legs of this sector. The angle between the two radii. So what is the area of this sector AOB? The green sector AOB. The area of sector AOB equals to the area of the circle that contains the sector, that is actually pi r square, r is the radius, times the angle between the legs of the sector, that is theta, over 360 degrees. Repeat again. The area of this sector AOB equals to pi r square, that is the area of the circle that contains the sector, times the angle between the legs of the sector, that is theta, over 360 degrees. So repeat again. In conclusion, we found out that a sector is a portion of a circle enclosed by two radii and the arc between them. And the area of the sector equals to pi r squared, that is the area of the circle that contains the sector, times the angle between the legs of the sector over 360 degrees. The angle is theta, of course. We use the new formula in order to find out the area of this sector, sector ABM. According to the formula that I presented to you, the area of this sector ABM will be equal to pi r squared. R is the radius of the quarter circle. That this is R is the radius of the quarter circle that contains the sector. So it is pi r squared, that is the area of the circle that contains the sector, times the angle between the legs of the sector, that is 53.13 degrees over 360 degrees. So in total we found out that the area of the sector ABM equals to pi r squared, that is the area of the circle that contains the sector, times the angle between the legs of the sector, that is 53.13 over 360 degrees. So here we have R is the radius of the quarter circle, is equals to 10. Therefore R squared is 10 squared, that is 100. Pi r squared is 100 pi. Times 53.13 over 360 degrees. In total, the value of this expression is equal to 46.3646 square units in its size. This is 46.3646 square units in its size. So if you found out that the area of this sector ABM equals to 46.3646 square units in its size. Our task is to find out the area of this lower segment BLM. So, what is the area of the lower segment BLM? This is the lower segment BLM. I'll prove it from here. This is the same segment BLM from the original drawing. We have to find out the area of the lower segment BLM. So, what is the area of the lower segment BLM? From the drawing, it is very easy to see that the area of the lower segment BLM equals to the area of sector BLM minus the area of triangle BLM. The area of sector ABM minus the area of triangle ABM. So as you know, the area of segment BLM, this is segment BLM, is equal to the area of sector ABM this is sector ABM minus the area of this triangle ABM. And again, the area of this lower segment BLM equals to the area of the big sector ABM minus the area of triangle ABM. It is very easy to see for the drawing that if you move the triangle from the sector, we get the segment BLM. Okay? If you move this triangle from this sector, we get the segment BLM. That is the segment that we are looking for. We already found out that the area of sector ABM equals to 46.3646 per unit in size minus the area of triangle ABM. We know that the angle between side AB and side AM is equal to 53.13 degrees. AB equals to 10 and AM also equals to 10. So in the next step, I present to you a new formula that will help us to find out the area of any triangle, and use the new formula in order to find out the area of this triangle ABM. This is triangle ABC that could be any triangle. Side AB or triangle ABC equals to A unit in its length, side AC equals to B unit in its length, and again between side AB and side AC is theta. So the area of this triangle ABC that could be any triangle equals to A times B, that is the multiplication of those sides by each other, times sinus the angle between those two sides, that is theta over 2. And again, the area of this triangle ABC that could be any triangle equals to A times B times sinus theta over 2. So we use the new formula in order to find out the area of this triangle ABM. According to the new formula, the area of triangle ABM must be equal to AB times AM, that is the multiplication of two sides by each other, times sinus the angle between the two sides, that is actually 53.13 degrees, divided by 2. This equation is the implementation of the new formula in our triangle ABM. So the area of triangle ABM equals to A times B, that is the multiplication of two sides by each other, times sinus the angle between those two sides, that is actually 53.13 degrees, divided by 2. AB is 10, AM is also 10, so AB times BM is 10 times 10, that is 100. Sinus 53.13 degrees is 0.8 divided by 2. 100 over 2 is 50, and 50 times 0.8 is 40. So in total, we should know that the area of this triangle ABM equals to 40 square units in its size. And we are looking for the area of this lower segment B and M. This B and M. So the area of sector B and M equals to the area of segment B and M equals to the area of sector ABM, that is 46.3646, minus the area of triangle ABM, that is 40. 46.3646 minus 40 is 6.3646. So we shall know that the area of this segment B and M is equal to 6.3646 units in size. This is the lower segment B and M. We found out that the area of this lower segment B and M is equal to 6.3646 units in size. In the next step, we'll find out the area of the upper segment BUM. In order to find out the area of the upper segment BUM, I copy this sector BOM, and in the page we analyze this sector BOM. the angle between the legs of the sector BOM is equal to 2 beta. This is 126.87 degrees in its size. The two legs OB and OM of sector OBM above the radii of the semicircle is equal to 5. So actually, this is sector BOM with the point from the original domain. According to the formula that I presented to you a couple of minutes ago, the area of this sector BOM will be equal to pi r squared. That is the area of the circle that contains the sector. R is 5. R is the radius of the semicircle, this is 5. So it is pi r squared times the angle between the legs of the sector, that is 126.87 degrees, divided by 360 degrees. R is 5, therefore r squared is 5 squared, that is 25, so pi r squared is 25 pi times 126.87 over 360 degrees. The value of this expression in total is equal here 25 pi times 126.87 over 360 degrees. In total, it is equal to 27.678 square units. So if you want to know that the area of this sector BOM is equal to 27.678 square units in its size. Our task is to find out the area of the upper segment BOM. This is the upper segment BOM, and we have to find out the area of this upper segment BOM. So what is the area of upper segment BOM? This is the upper segment BOM. Okay, this is the upper segment BOM. We have to find out the area of this upper segment. From the drawing, it is very easy to see that the area of this upper segment BOM, the green upper segment BOM, equals to the area of sector BOM minus the area of this triangle, triangle BOM. So write it down. The area of the upper segment BOM, it is equal to the area sector BOM this is sector BOM, the correct one here, minus the area of this triangle, triangle BOM. And again, the area of this upper segment BOM equals to the area of sector BOM minus the area of triangle BOM. we already found out that the area of this sector BOM equals to 27.678 square inches in size. So we have to find out the area of this triangle BOM. Note that angle BOM equals to 126.87 degrees in its size. BO equals to 5. OM also equals to 5. So according to the formula that I presented to you a couple of minutes ago, the area of this triangle BOM will be equal to BO times OM, that is the multiplication of two sides by each other, times sinus, the angle between those two sides, that is 126.87 degrees, divided by 2. BO is 5, OM is also 5, so BO times OM is 5 times 5, this is 25, times sinus 126.87 degrees, sinus 126.87 degrees is 0.8, divided by 2. 25 over 2 is 12.5, and 12.5 times 0.8 is 10. So in total we found out that the area of this triangle BOM equals to 10 square inches in its size. And the area of this upper segment BOM is equal to the area of sector BOM, that is 27.678 square inches in its size, minus the area of this triangle BOM, that is equal to 10 square inches in its size. 27.678 minus 10 is 17.678. So if you found out that the area of this upper segment BOM in total it is equal to 17.678 square inches in size. This is the upper segment BOM. Just found out that the area of this upper segment BOM is equal to 17.678 square inches in size. And the area of this region in total equals to the area of the upper segment BOM, that is 17.678, minus the area of the lower segment BLM, this equals to 6.3646 units in size. Pointing on. The area in the green shape that is the area that we're looking for in this question. This is the green shape. The area of this green shape is equal to the area of the upper segment BUM, that is equal to 17.678 is equals to 17.678 degree 17.678 square inches in size, plus the area of this lower segment being M, is equals to 6.3646 square inches in size. So in total, the area of this green shape equals to the area of the upper segment BUM is equals to 17.678 plus the area of the lower segment BLM is equals to 6.3646 square inches in size, and 17.678 plus 6.3646 in total is equal to 24.0426 currents in size. Equal to 24.0426 currents in size. And again, I'm sure although that the area that we are looking for this question, this is the area of this green shape. In total, it is equal to 24.0426 square units in size. So in the next step, I'll start the lecture. I'll start with the first question, of course. Our task in the first question is to find out the area of this green shape. So at the moment we have two squares. This is the big square TSQP. This is the small square ABCP. In addition, we know that this is quadrangle MBCP. This is equals to 27 square units in size, and this is triangle AMP. This is equals to 9 square units in size. Again, our task is to find out the area of this green shape. So first of all, we know that the area of this small square ABCP in total it is equal to 9 plus 27, that is 36. And again, the area of the small square ABCP. From one side it is equal to 36 square units in its size. But from the other side, we know that the area of any square equals to the length of one side squared. And therefore, the area of this square ABCP must be equal to the length of side AP squared. So from the other side, the area of the small square ABCP equals to the length of side AP squared. This is AP squared. And from this equation, AP squared equals to the area of the small square ABCP equals to 36. Equals to 36, we will know that AP squared equals to 36. Here we took out all the equation and found out that AP, the length of the missing side AP, is equal to the square root of 36, that is 6. So the length of this side AP is equal to 6 units. We know that all the angles inside the square are right angles, so all the angles inside this small square ABCP are right angles. Therefore, this angle must be equal to 90 degrees. And therefore, triangle AMP is a right angle. From one side, we know that triangle AMP equals to 9 square units in size. But from the other side, we know that the area of any triangle equals to the base AM times the height AP over 2. And again, from one side, the area of the right triangle AMP is equal to 90 square units in size according to what is given in the question. But from the other side, we know that the area of any triangle equals to the base AM times the height AP over 2. And from this equation, AM times AP over 2 equals to the area of the right triangle AP equals to 9. We will derive that AM times AP over 2 equals to 9. AM is the missing side, AP equals to 6. So we substitute AP by 6. And we actually found out that AM times 6 over 2 equals to 9. 6 over 2 is 3, so 3 times AM equals to 9. Here we divided the equation by 3 and finally found out that AM equals to 9 over 3, that is 3. So AM, this is side AM, that is equals to 3 units in its length. In the next step, I copied the right triangle AMP in a new page and implemented the Pythagoras theorem on this right triangle AMP. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So actually, this is the right triangle AMP that I copied from the original drawing. Side AM equals to 3, side AP equals to 6, and MP is the missing side, the missing hypotenuse. So in the right triangle AMP, according to the Pythagoras theorem, MP squared, that is the square of the hypotenuse, equals to MA squared plus AP squared. Repeat again, MP squared equals to AM squared plus AP squared. MP is the missing side, so we leave it as it is, so it is MP squared equals to AM squared. AM is 3, therefore AM squared is 3 squared, that is 9, plus AP squared. AP is 6, therefore AP squared is 6 squared, that is 36. So in total we should find out that MP squared equals to 9 plus 36, that is 45. MP squared equals to 45. Here we substitute 45 by 9 times 5, and we found out that MP squared equals to 9 times 5. Here we took out all those equations, and we found out that MP equals to the square root of 9, that is 3. So inside the root we have to leave 5. So MP in total equals to 3 times square root of 5 units inside. This is side MP, this is equal to 3 times square root of 5 units in its length. We know that what is the length of this line segment MB. From the drawing it is very easy to see that MB equals to AB minus AM. And again, MB equals to AB minus AM. We know that all the sides of this small square are equal to each other. MP is equals to 6, therefore AB must also equal to 6. So MB equals to AB, that is 6. Minus AM, that is 3. So in total, MB equals to 6 minus 3, that is 3. So the missing side MB equals to 3 units in its length. We know that those two angles are defined as vertex angles, and we know the vertex angles are equal to each other. So if we define the size of this angle as alpha, then the size of this angle must be also equal to alpha, because they are equal to each other according to the rule dimension. So in the big right triangle MAP or AMP, this angle equals to alpha, this angle equals to 90 degrees, and therefore this angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in a triangle. Likewise, in the small right triangle TMB, this angle equals to alpha, this angle equals to 90 degrees, and therefore this angle must be equal to 90 degrees minus alpha, according to the sum rule that the sum of the angles in a triangle is equal to 180 degrees. So the next step, we prove that those two right triangles are similar to each other according to angle similarity rule. It is very easy to see from the drawing, but I'll prove it anyway. So why those two right triangles are similar to each other? First of all, those two angles are both equal to alpha, and therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees, and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha, and therefore they are equal to each other. So if you found out that all the angles of the right triangle AMP are correspondingly equal to all the angles of this small right triangle TMB, and therefore those two right triangles are similar to each other according to angle similarity rule. So if you found out that the big right triangle AMP is similar to the small right triangle TMB according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side AP of the big right triangle AMP over side TB of the small right triangle TMB equals to side AM of the big right triangle AMP over side TM of the small right triangle TMB, and it is also equals to side MP of the big right triangle AMP over side MB of the small right triangle TMB. From the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side AP of the big right triangle AMP or side TB of the small right triangle TMB equals to side AM of the big right triangle AMP over side TM of the small right triangle TMB, and it is equals to side MP of the big right triangle AMP over side MB of the small right triangle TMB. AP is 6 over TB. TB is the missing side of electricities, and it is equal to AM. AM is 3 over TM. TM is the missing side of electricities, and it is equal to MP. MP is 3 over square root of 5 over MB. MB is 3. So in total, we found out that 6 over TB equals to 3 over TM equals to 3 times square root of 5 over 3. We have 3 in the numerator, 3 in the denominator, so 3 we can cancel, and we left only with square root of 5. So in total, we found out that 6 over TB equals to 3 over TM equals to the square root of 5. Those two sides are equal to each other, so we can get the first equation from those two sides that are equal to each other. So according to the first equation, 6 over TB equals to the square root of 5. Here we multiplied this equation by TB, and then we divided by square root of 5, and finally found out that TB equals to 6 over square root of 5 units in itself. This is side TB, that is equals to 6 over square root of 5 units in itself. Likewise, those two sides are also equal to each other, so we get the second equation from those two sides that are equal to each other. So according to the second equation, 3 over Tm equals to the square root of 5. Here we multiply this equation by Tm, and then we divide it by square root of 5, and finally found out that Tm equals to 3 over square root of 5 units in itself. This is side Tm, that is equals to 3 over square root of 5 units in itself. What is the length of side TP of the big square TSQP? From the drawing, it is very easy to see that TP equals to Tm plus MP. Again, TP equals to Tm plus MP. So TP equals to Tm. Tm is 3 over square root of 5 plus MP. MP is 3 times square root of 5. So again, Tm is 3 over square root of 5. MP is 3 times square root of 5. So in total, TP equals to 3 over square root of 5 plus 3 times square root of 5. So TP equals to 3 over square root of 5. Here we multiply this equation by square root of 5. And then we divided the square root of 5 in order to overcome factor with this number. So square root of 5 times square root of 5 is 5, and 5 times 3 is 15. So in total, the numerator we have 15 divided by square root of 5. It is allowable to multiply anything by 1. Square root of 5 or square root of 5 is 1, so we will not change the value of the expression by multiplying it by 1. Therefore, this operation is allowable. So in total, we should find out that TP equals to 3 plus 15, that is 18 over square root of 5. So in total, we should find out that TP equals to 18 over square root of 5 units in itself. This is side TP of the big square TSQP, and it is equal to 18 over square root of 5 units in itself. Our task is to find out the area of this green shape. From the drawing, it is very easy to see that the area of this green shape equals to the area of the big square TSQP minus the area of this triangle, small right triangle TMB, minus the area of this quadrilateral MBCP. And again, the area of the green shape in total equals to the area of the big square TSQP minus the area of the small right triangle, minus the area of quadrilateral MBCP. It is given as a equation that the area of this quadrilateral MBCP is 27 square inches in size, minus the area of this small right triangle TMB, minus the area of the small right triangle TMB. What is the area of the big square TSQP? The area of any square equals to the length of one side squared, and therefore it will be equal to TP squared. The area of the big square TSQP equals to the length of one side squared, that is to say TP squared, minus the area of this quadrilateral MBCP, that is 27, according to what is in the question, minus the area of the small right triangle TMB. The area of this small right triangle TMB equals to the base TB times the height TM over 2. And again, the area of the small right triangle TMB equals to the base TB times the height TM over 2. So the area of square TSQP equals to TP squared. TP is 18 over square root of 5, therefore TP squared is 18 over square root of 5 squared, minus the area of quadrilateral MBCP, is equals to 27, so it is minus 27, minus the area of the small right triangle TMB, is equals to the base TB. TB equals to 6 over square root of 5 times the height TM, that is 3 over square root of 5. Repeat again. The base TB is 6 over square root of 5. The height TM is 3 over square root of 5 divided by 2. So the area of the big square TSQL equals to 18 over square root of 5 squared. 18 squared is 324 over square root of 5 squared is 5. So in total, the area of the big square TSQP equals to 324 over 5 square roots in its size, minus the area of the quadrilateral MBCP, that is 27 according to what is given in the question, minus the area of the small triangle TMB, that is equals to, here we have 6 times 3 is 18, square root of 5 times square root of 5 is 10, square root of 5 times square root of 5 is 5, and 5 times 2 is 10. So in total, the area of the small right triangle TBM is equal to 18 over 10 square units in its size. 324 over 5 is 64.8, minus 27, minus 18 over 2 is minus 1.8. So in total, the area of the grain shape equals to 64.8 minus 1.8 is 63 minus 27. 63 minus 27 is 36 square units in its size. So we should find out that the area of this grain shape, that is the area that we are looking for this question, it is equal to 36 square units in its size. So we finished with the first question. In the next step, I presented you the second question and solve the second question of this lecture. Our task in the second question is to find out the area of this grain shape. So in the drawing we have square ABCD. We know that one side of square ABCD is equal to 10 units, and therefore all the other sides must be also equal to 10. In addition, inside this square ABCD we have the big quarter circle and the semicircle. The diameter of this semicircle is BC, that is 10. We define the center of this semicircle, this point as point O. If the diameter is 10, then the radius must be equal to half of it. That is to say, it is 10 over 2, that is 5. The radius of B is 5, the radius of C is also 5. This is point A, that is the center of the quarter circle. Point B is the point on the quarter circle itself. Therefore, AB is the radius of the quarter circle, that is equal to 10. Likewise, AD is also the radius of the quarter circle, that is equal to 10. So, in the next step, we define the intersection point between the quarter circle and the semicircle. This point is point M, and we join points A and M together by a straight line. Point A is the center of the quarter circle, point M is the point on the quarter circle itself, therefore AM is the radius of the quarter circle, that is equal to 10. But AM is actually 970 AM is a tangent to the semicircle at point M. In the next step, we join points O and M together by a straight line. Point O is the center of the semicircle, point M is the point on the semicircle itself, therefore OM is the radius of the semicircle, of this semicircle, that is equal to 5 units. Here we can implement rule 1 because we have the radius OM of the semicircle that is equal to 5. The radius OM is 1 to point M, that is the point of tendency of tangent AM with this semicircle. And remember, your radius is 1 to the point of tendency, then tangent AM will be perpendicular to the radius MO. If AM is perpendicular to MO, it means that this angle equals to 90 degrees according to rule 1. In the next step, we join points A and O together by a straight line. We know that all the angles inside and square are right angles, so this is a right angle. It is 1 out of 4 angles in square ABCD, and therefore it is equal to 90 degrees in its size. So in the next step, we join points A and O together by a straight line. By joining points A and O, get those two right angles. We have the right triangle ABO and the right triangle AOM. So in the next step, we prove that those two right triangles can go into each other according to side rule. So why those two right triangles can go into each other? First of all, side BO equals to side OM. They are both the radii of the semicircle, that is equal to 5, and therefore they are equal to each other. In addition, side AB of the right triangle ABO equals to side AM of the right triangle AOM. They are both there, they have the quadrilateral segment that is equal to 10, and therefore they are equal to each other. And finally, side AO is a common side that belongs to both triangles, so we can write down that AO equals to itself, it's a common side that belongs to both triangles. So we should prove that all the figures of the big right triangle ABO are correspondingly equal to all the figures of the big right triangle AOM, and therefore those two, again, all the three sides of the big right triangle ABO are correspondingly equal to all the three sides of the big right triangle AOM, and therefore those two right triangles can go into each other according to side rule. And again, if you found out that the big right triangle AOB congruent, this is the side of congruent to the big right triangle AOM according to side rule. And from the fact that those two right triangles can go into each other, we know that those two angles must be also equal to each other according to the rule that corresponding angles in congruent triangles are equal to each other. Those two triangles can go into each other, and therefore those two angles must be also equal to each other in their sizes. So if we define the size of this angle as alpha, then the size of this angle must be also equal to alpha because they are equal to each other. Likewise, from the fact that those two right triangles can go into each other, we know that those two angles must be also equal to each other according to the same rule that corresponding angles in congruent triangles are equal to each other. So if we define the size of this angle as beta, then the size of this angle must be also equal to beta because they are equal to each other according to the rule that I mentioned. So in the next step, I copied the right triangle ABO in a new page and implemented the Pythagoras theorem on this right triangle ABO in order to find out the length of the hypotenuse AO. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the square. The square of the hypotenuse equals to the sum of the squares of the perpendiculars. So this is the right triangle ABO that I call from the regular domain. This right triangle ABO, according to the Pythagoras theorem, AO squared, that is the square of the hypotenuse, equals to AB squared plus BO squared. AO is the missing side, so we leave it as AO is the missing side, so we leave it as it is. So it is AO squared equals to AB squared. AB is 10, therefore B squared is 10 squared, that is 100, plus BO squared. BO is 5, therefore BO squared is 5 squared, that is 25. So in total, we should find out that AO squared equals to 100 plus 25, that is 125. We substituted 125 by 25 times 5. We found out that AO squared equals to 25 times 5. Here we took a root out of this equation, and we found out that AO equals to the square of 25, that is 5. So inside the root, we left only with 5. So in total, we found out that AO equals to 5 times square root of 5 units in its length. This is the missing hypotenuse AO, that equals to 5 times square root of 5 units in its length. We know that the sum of the angles in any triangle is equal to 180 degrees, and therefore the sum of the angles in this right triangle ABO must be equal to 180 degrees. So which angles we have the right triangle ABO? We have alpha plus beta plus 90 degrees, in total must be equal to 180 degrees. In the right triangle ABO, the sum of the angles must be equal to 180 degrees. That is to say, alpha plus beta plus 90 degrees, in total must be equal to 180 degrees. Here we subtract the 90 degrees from this equation, and we found out that 180 degrees minus 90 degrees is 90 degrees. So alpha plus beta equals to 90 degrees. Here we subtract alpha from this equation, and we found out that beta equals to 90 degrees minus alpha. We continue to focus on this right triangle ABO. In the right triangle ABO, sinus alpha equals to BO over AO. Again, sinus alpha equals to BO over AO. And again, in the right triangle ABO, sinus alpha equals to BO over AO. BO is 5, AO is 5 times square root of 5. BO is 5 and AO is 5 times square root of 5. So in total, sinus alpha equals to 5 over 5 times square root of 5. We have 5 denominator, 5 denominator, so 5 will get cancelled. We left only with 1 over square root of 5. So in total, we actually found out that sinus alpha equals to 1 over square root of 5. Our test is to find out the value of angle alpha itself, the size of angle alpha. In order to find out the size of angle alpha, we operate on the result of sinus alpha, that is 1 over square root of 5, the opposite function of sine, that is arc sine. In this way, we get the value of angle alpha itself. So we operated the opposite function of sine, that is arc sine, on the result of sinus alpha, that is 1 over square root of 5. In this way, we got the value of angle alpha itself. And arc sine 1 over square root of 5 is 26.565 degrees. So in total, we should find out that angle alpha equals to 26.565 degrees in its size. if alpha equals to 26.5 if alpha equals to 26.565, it means that 2 alpha must be equal to 2 times 26.565. This is actually 53.13 degrees. We already found out that beta equals to 90 degrees minus alpha. Here. Beta equals to 90 degrees minus alpha. So beta equals to 90 degrees minus alpha. And we already found out that alpha equals to 26.565 degrees. So 90 degrees minus 26.565 degrees is 63.345 degrees. So in total we found out that beta equals to 63.435 degrees, and therefore 2 beta equals to 126.87 degrees in size. So in total we found out that 2 alpha equals to 53.13 degrees in size, and 2 beta equals to 126.87 degrees in size. This is angle 2 alpha, this is angle BOM. This equals to 53.13 degrees in size. And this is the big angle AOB. This equals to 2 beta. 2 beta equals to 126.87 degrees in size. Our task is to find out the area of this screen shape. So in order to find out the area of this screen shape, we join points M and B together by a straight line. By joining points M and B, we divided this green shape into 2 parts. This is the first part and this is the second part. The first part is the upper segment MUB, and the second part is the lower segment MLB. So we calculate the area of each segment separately, then we add the 2 areas with each other, and this will be the area of this green shape. So first of all, we calculate the area of this lower segment MLB. In order to find out the area of this lower segment MLB, I copied sector AMB in a new page, and we analyze this sector AMB. This is the sector AMB that is coming from the original domain. This sector AMB, this is angle 2 alpha, that is equal to 53.13 degrees in its size. AB equals to 10, AM also equals to 10. Now actually the legs of the sector. So first of all, what is a sector? A sector is a portion of a circle. This is sector AOB. It is a portion of a circle enclosed by 2 radii and the arc between them. And the 2 radii defined as the legs of the sector, and the angle between the legs of the sector is theta. And the area of this sector AOB equals to pi r squared, that is the area of the circle that contains the sector, times angle theta over 360 degrees. Repeat again. The area of sector AOB equals to pi r squared times angle theta over 360 degrees. So we use the new formula in order to find out the area of this sector AMB. According to the formula that I presented to you, the area of this sector AMB must be equal to pi r squared, which is the area of the circle that contains the sector, times the angle between the legs of the sector, that is 53.13 degrees over 360 degrees. Repeat again. The area of this sector AMB equals to pi r squared times 53.13 over 360 degrees. R is 10. R is the radius of the quarter circle, that is 10. So r squared is 10 squared, that is 100. So pi r squared is 100. And it is 100, pi r squared is 100 pi times 53.13 over 360 degrees. So in total, the value of this expression 100 pi times 53.13 degrees over 360 degrees, in total it is equal to 46.3646 coordinates in size. So in total we found out that the area of this sector AMP equals to 46.3646 coordinates in size. Our test is to find out the area of this lower segment BLM. So we have to find out they have this lower segment BLM. What is they have the lower segment BLM? From the drawing it is very easy to see that they have this lower segment BLM equals to the area of the big sector A and B minus the area of triangle A and B. Then again, they have segment BLM, the lower segment BLM equals to the area of the big sector A and B minus the area of triangle A and B. It is very easy to see that from the drawing that if you remove from this sector this triangle, you will get the lower segment BLM. Therefore, the area of segment BLM equals to the area of sector A and B minus the area of triangle A and B. Okay? We already found out that the area of this sector A and B equals to 46.3646 units in size minus the area of this triangle A and B. I presented to you a new formula that will help us to find out the area of any triangle. So, this is triangle ABC that could be in a triangle. In triangle ABC, side AB equals to A units in its length, side AC equals to B units in its length, and the angle between side AB and side AC is theta. According to the new formula, this triangle AB that could be in a triangle equals to A times B times sinus theta over 2. And again, the area of this triangle that could be in a triangle equals to A times B, that is the multiplication of those two sides by each other, times sinus triangle between those two sides, that is theta over 360 degrees. Repeat again, the area of this triangle ABC equals to A times B times sinus theta over 2. We use the new formula in order to find out the area of this triangle A and B. According to the new formula, the area of this triangle A and B equals to side AB times side AM times sinus triangle between those two sides, that is 53.13 divided by 2. Repeat again, in total, the area of this triangle ABM equals to AM times AB times sinus 53.13 degrees over 2. AB is 10, BM is 10, so AB times BM is 10 times 10, that is 100. Sinus 53.13 is 0.8 divided by 2. 100 over 2 is 50, and 50 times 0.8 is 40. So in total, we found out that the area of this triangle ABM equals to 40 square units in its size. And in total, the area of this segment BNM equals to the area of sector ABM, that is 46.3646, minus the area of this triangle ABM, that is 40. 46.3646 minus 46.3646 square units in size. So in total, we found out that the area of the lower segment BNM is equal to 6.3646 square units in size. In the next step, we calculated the area of the upper segment BUM. In order to find out the area of this upper segment BUM, I copied this sector BOM in the new page and analyze this sector BOM. So actually, this is sector BOM that I copied from the original drawing. This is equal to beta, that's equals to 126.87 degrees in its size. OM equals to OB, they are both the radius of the same circle, that is equal to 5. So the two legs of the sector, each of them is equal to 5. So according to the formula that I presented to you a couple of minutes ago, the area of this sector OBM must be equal to pi r squared, that is the area of the circle that contains the sector, times the angle between the legs of the sector, that is 126.87 degrees over 360 degrees. So the value of this expression, 25 pi times 126.87 over 360, in total it is equal to 27.678 square units in size. So we should find out that the area of this segment BOM, in total it is equal to 27.678 square units in size. Our task is to find out the area of this upper segment BOM. So the area of the upper segment BOM equals to the area of the big sector BOM minus the area of triangle BOM. It is very easy to see from the drawing that if you remove from this sector BOM this triangle, we get segment BOM. That is the segment that we are looking for. Therefore, the area of segment BOM equals to the area of sector BOM minus the area of triangle. If you remove the triangle, you get the segment. We only found out that the area of sector BOM equals to 27.67, and the area of this triangle BOM equals to the multiplication of two sides by each other, that is BO times OM. BO is 5, OM is 5, therefore 5 times 5 is 25, times sinus angle 126.87, that is 0.8 divided by 2. So in total, there are of triangle BOM equals to 25 times 0.8 over 2. 25 over 2 is 12.5, and 12.5 times 0.8 is 10. So in total, we should find out that the area of this triangle BOM equals to 10 square units in its size. So in total, we should find out that the area of this upper segment BOM equals to the area of sector BOM minus the area of triangle BOM. The area of sector BOM is 27.678 minus the area of this triangle BOM, that is 10 square units. 27.678 minus 10 is 17.678 square units in size. So in total, we should find out that the area of this upper segment BUM equals to 17.678 square units in size. Our test is to find out the area of this sector. Our test is to find out the area of this green shape. So the area of this green shape equals to the area of the upper segment BUM, that is 17.678, plus the area of the lower segment BLM, that is 6.3646 square units in size. So in total, the area of this green shape equals to the area of the upper segment BUM, that is 17.678, minus the area of the lower segment BLM, that is 6.3646 square units in size. So 17.678 plus 6.3464, in total it is equal to 24.0426 square units in size. So in total, we should know that the area of this green shape, that is the area that we are looking for in this question, is equal to 24.0426 square units in size. Okay, thank you very much.